Today we're at NASA's Glenn Research Center, where we're looking down the barrel of the gun at their Ballistic Impact Research Lab. Joining me is Matt Mellis, a research scientist here at Glenn. Can you give us a little bit of the history of this laboratory and how this experiment operates?
I sure can, John. What you're looking at here is our 12-inch barrel that we have on our big ballistic impact gun. You'll see the small gun later as we tour the lab. The Ballistic Impact Laboratory and the team that goes with it has been here for roughly 15 years. We started in the mid-90s, and one of our primary research goals was to do research on jet engine debris mitigation, fan containment, bird strikes, ingestion of particles inside of jet engines that could cause harm or compromise the engine itself during operation. And while we were trying to make engines safer, we also were trying to reduce weight and increase efficiency, which is often a balancing act in that world. So what you're seeing here is our large impact gun, and it works very simply. Is just a pressurized vessel, as you see behind you. This big black vessel is pressurized with nitrogen gas. It has a mylar, what we call a mylar burst disc on it that has a nichrome wire that's attached at two ends that can be hooked up to an electric current. So we push the whole pressure vessel together into the barrel here, and obviously something is loaded in the barrel. And the pressure vessel holds all the pressure in it until we run a current through that wire, at which time the vessel's compromised. We run a current, heats up, compromises the vessel, and propels that sabot with the projectile in the barrel down to the business end of the gun at the other end. We'll go down and see that in a few minutes.
When people think of bird strikes, they don't think of birds as being particularly dangerous, but obviously they can have a dramatic impact on a jet engine. Can you talk a little bit about that and why that's the case?
Absolutely. You know, probably the most notable current event that happened with bird impacts were an Airbus that was brought down by ingesting Canadian geese, a flock of Canadian geese, into both engines, and both engines simultaneously were compromised, and the pilot had to land in the Hudson River in New York City. An amazing event, because not a single passenger was harmed on the landing, which was fantastic. So that is an example of bird impacts and bird strikes and the damage that they can cause to engines. That was unusual because most bird impacts are a singular event, one or two or three birds being hit as opposed to a flock per se. But the engines are designed to handle that event, and then the engines also have to be designed to be able to shut down safely without any threat to the vehicle, so they can fly back on the other good engine, which normally is the case. There's usually an engine left over, and few people probably know that any commercial jet aircraft can fly on just one engine with no problem.
You're obviously not launching birds down this tube, so how do you simulate a bird strike?
That's a great question. We do it very safely and very humanely. So it's basically a gelatin cylinder, if you will. If we're testing for small birds, it's maybe an inch in diameter by 3 inches long, and if it's larger birds, it's about the size of a large soup can, and that represents a seagull-sized bird. 10 years ago, actually, just a few months back, was the anniversary of the Columbia tragedy, where we lost the orbiter Columbia and 7 of her crew members. And for about 4 years, this team and this laboratory was committed to finding out the cause of the accident and getting NASA's shuttle fleet back to flight. Columbia was an accident that happened as a result of an impact event, and a piece of insulating foam that really was as light as a feather had come off of the external tank, which is the cryogenic fuel tank for the space shuttle main engines. That foam had separated from the tank, and it decelerated by the free stream air rushing over the shuttle as it was launching, and it hit the left wing of the orbiter and caused some sort of damage in the wing leading edge thermal protection system. 2 weeks later on re-entry, they came back, and hot plasma gas got in through that damaged site and compromised the wing, and ultimately we lost the vehicle and the crew. So our research over the several years following the accident, number one, found out what the cause of the accident was and supported the investigation team's findings. And then number two, we went back and made sure that our vehicle would never be compromised by a debris strike again. And so we did an enormous amount of impact testing in the facility next door to better understand what the threat was to our vehicle and eliminate it if it was a threat beyond what was acceptable to us.
What other types of projectiles have you launched here?
A lot of things that we test are, there's a combination of actual component testing, which looks more real to the outside viewer, where we actually take real fan blades and put them in the gun and then shoot the fan blades into a jet engine fan containment structure. It's basically, it looks just like the front end of a jet engine. That would be a component test, but then we do a lot of fundamental testing where we might put something as simple as a flat panel down there, and we would shoot some kind of representative blade article into the flat panel. The idea being we would be trying to see the amount of energy that particular panel would be able to absorb. Now, the real emphasis in recent years is to move away from metal structure that protects against impact events and go to composite structure. Composites are often talked about in all walks of life now, from sporting goods to jet aircraft. And we're even going to what we call a soft wall structure, which is kind of like a Kevlar bulletproof vest, if you will, a fabric structure that protects against impact events. And those are amazing because we can reduce the weight by an order of magnitude or more just by going to fabric as opposed to a steel wall.
What types of projects are you looking forward to in the future? Is there any applications that maybe you haven't been able to try yet that you'd like to see happen down the road?
Well, NASA Glenn, as most NASA laboratories now, strives to partner with outside entities to collaboratively make things better on an engineering basis. And so this lab will always be a testing spot for people to come in and test their materials or their components to identify just how good they are. So there'll be a lot of work that's similar to what's going on now, but there's a lot of exciting work that's more unique. For example, we're interested in maybe looking into ice impacts, and I think we'll give you guys some footage on that where we look at the phenomena that occurs from ice impact. Now, why is this interesting to us? Because ice exists in space on asteroids and on other planets, and understanding the phenomenon of ice impact may help us in that area to better understand how to deal with ice once we get up into space with space operations. So those are just two examples of where we might go. But the third sort of response to that question is it's anybody's guess. Just around the corner is going to be some exciting research topic that could be suggested or we could come up with on our own, and we'll be testing that because we have all the equipment to do so.
Have there been any results that have been surprising to you so far where an experiment perhaps turned out in a completely different way than how you'd predicted?
You know, ice research was interesting because we really didn't have an intuitive understanding of how ice would behave in a ballistic environment. It's a very interesting phenomenon, and you'll see that in the footage where you see the shock wave go through and it immediately crystallizes the ice, and then now you have this almost fluidic mass of ice crystals moving where once you had a solid piece of ice. So that's actually one of the most interesting things, is to watch that phenomenon unfold. Fabric behavior is also quite interesting, and I think actually the bird strike behavior with the simulated bird projectiles is very dramatic. It's a highly dynamic event, and it's completely unintuitive. When you see it, you can't believe it. So this disc was originally two flat pieces of mylar, and it was held up against the pressure vessel. And these are the bolt holes, and so when they put the whole thing together, the two flanges join, and all of the pressurized nitrogen remains inside the pressure vessel and is released almost instantly when they put the current through the nichrome wires, and it melts the disc, and away you go.
So obviously you'd be interested in tracking the movement of these projectiles as they actually impact your target. Can you talk a little bit about how you do that?
Right. This is a great example of that. This is a simulation blade, as you see here, and you see it has a number of dots and little X's and fiducials, as some people might call that in the industry. And we use a very clever capability that exists in industry right now commercially that uses two cameras to track motion and dynamics by taking pictures of an object from two different points of view. We do this every day with our eyes. All right, so we can sense depth with our eyes, and our brain does the calculations, to give us a sense of depth. Well, the cameras can do that, and on digital photography, we can actually write software that calculates exact motion measurements. And in this case, we would track these dots, and we would track velocity, translation, rotation, and decelerations, all by just snapping pictures from two different points of view. And in fact, this is a nice simulating fan blade that we would use for a generic test. And this is one that's been used. It gives you a sense of a little more wear and tear, if you will. from the impact event that took place. So this is two examples of how we use dots to track. We can also track motion of the panels as they undergo impact. And so as you look around the laboratory, you're going to see a lot of our test panels having dots on them. And so using that same stereo camera pair system, what we can do is we can actually track the deformations to micron levels of accuracy as this panel undergoes deformation from the impact event. It's an enormous tool for us to evaluate our panel integrity as it undergoes impact. So that's what these dots are all about, and that's how we track motion. All right, John, so let's take a look at the business end, as I like to call it, of the ballistic impact gun. What we've got here is a test setup for jet engine fan containment testing. As I said earlier, we do a lot of different types of testing, but this particular configuration is for jet engine fan containment. And what happens is they bring a big containment structure in here which sits on this mandrel, and then the blade, as it is shot, crosses over the upper end and hits the lower end, as you can see here, and it tests whatever the structure is that we want to see how it holds up under impact. So that's what this is. Now I can show you a little bit about how we actually get the blade into the gun. As I had earlier in the piece, talked about this being one of the typical blades that we shoot. We mount this into this aluminum can that's called a sabot. And the sabot basically enables us to, if you will, orient the blade in exactly the configuration that we want it. So it's held in there like so. And when we fire the gun, the blade and the sabot come down the barrel all at once, and then it hits inside this plate here. So it stops the can in its tracks. The can stops behind this, all right, and actually becomes destroyed in that action. It's shredded and bent up pretty good. And the blade continues out of the barrel, crosses over the upper end, and impacts into the fan containment structure. So that's how that works. That's how that all comes together. Very fast, I might add, in a big, loud explosion.
About how fast is the blade traveling when it comes out of the barrel?
We're shooting typically on the order of about 1,000 or 1,100 feet per second, which is roughly in the neighborhood of 700 miles an hour. So it's pretty fast. It's more fast than the naked eye can see. And that's why we have these high-speed cameras to document the test so we can see exactly what went on.
Can you orient this test stand into different angles to do different types of tests?
Absolutely. If you look at the floor, you can see that we've got these keyholes in the floor so we can mount this structure any way we want. We can set up the angle any way that we want and do a lot of different configuration testing. So we have total flexibility in this facility to do pretty much any kind of testing that we want to do from an impact standpoint.
I see a lot of debris around in a part of the structures. What is that from?
That's actually our bird simulation material. Again, it's kind of hard and crunchy now because it's been here for a while and dried out, but it's actually food grade gelatin that is mixed up just like you would mix Jell-O, and it sets up. And so when the impact takes place, a lot of the fragments shoot around the facility and actually stick to the wall. So that's one of the things that we have to clean up periodically, and we don't quite get all of it, which is why you see some of it here still.
So we've now moved to the other side of the Ballistic Impact Lab to take a look at their smaller gun. Joining me now is Dwayne Revelock, and he's going to walk us through how this machine operates. Dwayne, can you tell us a little bit about this experiment here?
Yes, this is our small vacuum gas gun. We shoot smaller projectiles. Typically we'll use a sabot, which is our projectile carrier, and a lot of times we'll shoot just foam. So this gets loaded into the sabot, and the sabot will get shot down this long barrel, and the sabot is stopped at the end. The foam will come out and hit whatever target we're shooting at.
Dwayne, could you walk us through the process of setting up the gun and actually doing a ballistic impact?
Sure. We have Jeff Hamill, our technician. He's actually one who loads the gun and shoots it for us. He's actually going to load the projectile now.
So he has the dots up, and that's so that the two camera tracking can image what's going on as it impacts the...
Yeah, for this test we have two cameras mounted on top of the chamber, and they're the stereo pair, and they'll be able to see those dots on top of the projectile to measure its orientation as it hits our panel.
So now he brings the gas chamber in contact?
Yes, it brings in contact, and the plastic sheets you see there is the Mylar. There's a nichrome wire we run around it, and we want to fire, we run a current to the wire so it heats up like a toaster wire, melts the plastic, releases the gas from the chamber, pushes a projectile down the barrel.
All right, 25 psi, 3, 2, 1.
So we can go in and get our projectile we just shot. You can see there's not much damage to it, but it did damage the panel we were shooting.
And we shot at a fairly low pressure at 25 psi, and you typically fire at much higher pressure, is that correct?
Yes, well, for this material we're testing, it's a lower speed to penetrate it. The projectile was going around 400 feet per second. So still a low pressure, light projectile. You get a high speed from it.
Well, thank you, Dwayne, for the demonstration showing us how your instrument works.
Thanks. We're glad to have you out here.
The scientists here in the Ballistic Impact Lab are working to make air travel safer and potentially influence the design of future jet engines. Join us next time as we venture to the Compass Engineering Lab at NASA's Glenn Research Center and witness firsthand how NASA engineers designed the next generation of spacecraft, all on tomorrow's discoveries.